Welcome to Form Tolerance. In part 1, we discussed about straightness and fatness. We will continue to talk about roundness and cylindricity in this video. First, let's look at roundness tolerance, also known as circularity tolerance. Roundness or circularity is a 2D version of cylindricity tolerance. It shows how close a part should be to a perfect circle. There are two roundness tolerance called out in the drawing. So this is the roundness symbol and this is the tolerance value. Note that there is no any diameter symbols attached to the tolerance value. It's because 0.1 is the difference of radius between two concentric circles. Also, there is no datum reference like others from tolerance. So you can also see that the leaders is pointing at the surface. Generally, roundness tolerance comes to mind when we want to know how well a cylinder can be rolled on a flat surface. Let's have a look on the tolerance zones, how roundness can be interpreted. Two roundness tolerance are called out. One is on the cone side in plan 1 and another one is on the cylinder side in plan 2. Let's cross-cut the plan 1 to see the tolerance zone. You can see that there are two concentric circles with a distance of 0.1. The yellow color part surface must be lie between the tolerance zone. Also in plan 2, the tolerance are formed by two concentric circles. As long as the yellow curve fall between the tolerance zones of a distance of 0.1, then this is within the spec. It is to be noted that the outer circles and inner circles are not necessary to have an equal distance to the exact circles. The orange color is the exact circles. You can see that the outer circles has a slightly bigger distance compared to the inner circles in this cross section. As long as the innermost point and the outermost point are all within this tolerance zone, then this is within the spec. Also, the two tolerance zones are perpendicular to the part axis. Since the call is applied on one cross section, so it might be a limitation for the roundness tolerance. In this cross section, maybe the true profile can be fall within the tolerance zone, but it might not be possible for every single cross section along the length of the cylinder. For instance, certain portion of the cylinder might have a flat surface or uneven surface. That's why during the measurements, when we put the part on the turntable or the V-block, we will place the digital dial in few more cross-section. Yes, it is not practical or possible to place in every cross-section, but it is the usual practice or the problem in roundness measurements. Now we learn about the basics of roundness tolerance. Next, let's see what is the advantage of using. In order to control the form of the circles in this cross-sectional plan, we may just control the size tolerance. Namely, we can tighten the tolerance of the diameter. So we no need to apply the GDT. So in this example, we may just need to revise the tolerance from 0.2 to 0.05. So with this, we can achieve the variance of the circles in the zone of 0.1 mm. So why we still need GDT? Because in certain cases, the diameter is not our main interest. Our main concern is just on the variance of the circles. We want to maintain the form of the circles as perfect as possible. So in these cases, so we can apply the GDT and then we can lose our diameter tolerance. So by applying the roundness tolerance in these cross sections, now we can revise the tolerance to 0.2 or even 0.5. Therefore, with GD&T, we can save the manufacturing costs to make an expensive shaft with an accurate diameter. You might be thinking, line profile also can use to control the form of the circles instead of roundness. Roundness usually control the variations of the circular shape, while line profile also control the variations of the true profile. So what is the difference? We usually have tendency to use the roundness callout to control the circular shape. Though it is not wrong to use the line profile, but it's more common to use the line profile in some more compressed random profile. When dealing with circles, the roundness callout is still the first choice. Looking closer at the tolerance zone, the tolerance zone is constructed by two concentric circles. Thus, two concentric circles is not necessary to be equidistant from the exact circles. So, in fact, the outer circles is further away from the exact circles compared to the inner circles. As long as all the innermost and outermost point of the yellow curve fall within the tolerance zone, it can fulfill the tolerance requirements. Now let's only focus on the variations of the circles. It's not really care about the diameter. On the other hand, the tolerance zones of light profile is tied to the exact circles. The distance from exact circles to the outer circles and inner circles is the same. Therefore, line profile also control the absolute size other than the variations of circles. Now let's only focus on the variation. It is less stringent and more flexible compared to the line profile. That's why it is a better option when we want to control the circular shape. That's all on roundness tolerance. Next, we will move to the last topic of form tolerance, cylindricity. Roundness tolerance controls the shape of circles at a single cross-sections. The call at the cross-sections is independent from those in other cross-sections. If you want to control all cross-sections along the length of the cylinder, you need to choose cylindricity over roundness. Cylindricity is the 3D version of roundness tolerance and is the combination of straightness and roundness. From the drawing, here is the cylindricity callout. The leader is applied on the surface of the cylinder. Same as roundness, there is no diameter symbol attached to the tolerance value, and also no datum reference. An example of cylindricity application is when we want to pass through a shaft through a hole. Let's look at the tolerance zones of cylindricity callout. The tolerance zone is limited by two coaxial cylinders with a distance of 0.1 apart. The edge surface of the cylinder must be limited between these tolerance zones. You can see that cylindricity not only controls the surface of the part, it also controls the axis of the part. During measurement, the digital dial will be moved along the shaft to assess how close the shaft conforms to a perfect cylinder. Similar to roundness, cylindricity controls the variance of the surface, but not control the diameter. Therefore, it offers a great manufacturing cost reductions. Let's see an example. In order to achieve the tolerance zones with a distance of 0.1, the size tolerance can be controlled. We can revise the tolerance to plus minus 0.05 so that we can achieve the tolerance zones with a distance of 0.1. But as mentioned, these methods will create a very expensive cylinder. That's why we have another method which is using the GDT. So here we apply the cylindricity with a tolerance values of 0.1. With GDT, now we can revise the tolerance. We can revise the tolerance to 0.2. So with this, we can save our manufacturing costs. Before wrapping up cylindricity, let's make a comparison between roundness and cylindricity. Roundness talk about how perfect is the circus. Cylindricity define how perfect is the cylinder. Roundness is fine as long as the shaft is round enough, while cylindricity will make sure the shaft round enough and straight along the length of the shaft. Roundness is the 2D tolerance focused on a single circus, while cylindricity is a 3D tolerance which control the multiple circles through the cylinder. This means that roundness control the variance of the circles on the cross-sectional plane, while cylindricity control every circular cross-sections along the entire length of the cylinder. Both control the variations of the surface, but cylindricity also control the axis indirectly since it controls the circular cross-sections along the entire length of the cylinder. Lastly, the tolerance zones of roundness is constructed by two concentric circles, while the tolerance zones of cylindricity is constructed by two concentric cylinders. We have run through the all four foam tolerance. That's all on my end. See you in my next GDT video. Thanks for watching.